Welcome back to Before Basics Computing. I wanted to go over binary and hexadecimal briefly before we get too far into the live streams, just because I will be using it a lot and I'm not reviewing it there. So many other people on YouTube have explained binary before, so if you don't understand my video, I would recommend you look on YouTube. There's a link down below to one I recommend, and there's many others if you still don't understand it. If you already know about binary and hexadecimal, then feel free to skip this video, though you might find it a good refresher. Alright, let's get into it. At its core, binary and hexadecimal are just other ways to represent numbers using different digits. There are an infinite number of ways to represent numbers. For example, Roman numerals. The reason we use binary with computers is digital computers can only represent two things per storage unit, such as 0 and 1, false and true, yin and yang. We don't usually use that last one, but we could. We will be using 1 and 0 as our representation of choice, as it pertains to numbers. Let me go over some definitions before we get started. First, the most significant digit is the digit with the largest place value, and is usually the leftmost digit of a number. The least significant digit is the digit with the smallest place value, and is usually the rightmost digit of a number. Bit can also be used in our context as another word for binary digit. The percent symbol before a number will denote that it is a binary number, and the dollar sign will denote a hexadecimal number. These are fairly commonly used standards, and that's why we use them here. First, let's go over the number system we all know and love, decimal. When we count in decimal, a singular digit can only represent 10 different numbers, 0 through 9. This is the ones place. But what happens if we add another 1 to 9? Well, it rolls over to our first value and becomes a 0. If we want to represent a number larger than 9, we need another digit. Did you see what just happened here? Normally we ignore this second most significant digit if it is a 0, but since we are using a fixed number of digits, it helps to show it. Now when we add 1 to the 9, we carry the 1 and add that to our next digit, and we get 10. And if we count up another 10, we get 20, and so on. Because every number in this place represents another 10, it is called the tens place. And so on and so forth. We can continue adding digits until we need another digit to represent 100. This new digit is called the hundreds place and keeps track of the number of hundreds that we have. So now that we have all this, what could we say about a number like 234? Well, we could say we have 2 100s, 3 10s, and 4 1s, giving us 234. Now, you might notice a pattern here. Each place value is the place value right before it times 10. This is because we are in base 10. So, if we look at it, we have ones place, tens place, hundreds place, thousands place, 10,000s place, and so on. We can also find out how big of a number we can hold in a limited number of digits by taking the value of the next digit and subtracting by 1. So with 2 digits, we can only hold 99, since the next place is 100. And so if we subtract 1, we get 99. This formula will hold true for the other bases as well. So now that we have taken a deep look into how the number system we use every day works, let's dive into binary. When we count in binary, a singular digit can only represent two different numbers, 0 and 1. This is still the ones place. And the same thing that happens in decimal happens here. If we add 1 more to 1, it rolls over to the first value and we get 0. So let's add on another digit. Now, when we add 1 more to the 1, we carry the 1 and add that to our next digit, and we get 10. This new digit is the 2's place, and it counts how many 2's we have. We can continue counting for a little while, but not for long. We can now roll over once we reach 1, 1, or decimal 3, as we now have 1, 2, and 1, 1. Let's add 2 more digits. The 3rd counts how many 4's we have, and the 4th how many 8's. So now, if we have a binary number like 1, 1, 1, 1, we have 1, 8, 1, 4, 1, 2, and 1, 1. If we add these together, we get decimal 15. Let's just do another random number, like 1010. This says we have 1, 8, 0, 4's, 1, 2, and 0, 1's. Add that together, and we get decimal 10. But wait, we just converted from binary to decimal. And yes, it's true. This is how easy it is. Take your place values, and if you had one, add it, and if not, don't. Like the base 10 system, each place value is the place value right before it times 2, since we are in base 2. So an 8-bit value has the 128's place, the 64's place, the 32's place, the 16's place, the 8's place, the 4's place, the 2's place, and finally the 1's place, where every base begins. So a value like 10010011 has 1 128, 0 64's, 0 32's, 1 16, 0 8's, 0 4's, 1 2, and 1 1. If we add that all together, we get decimal 147. So now we know how to convert from binary to decimal. But what about decimal to binary? Well, let's start with an easy number, 11. I know this fits into 4 bits. Because of this, we can start at the 8's place. We ask, how many 8's are there in 11? Well, 1. So we take an 8 out and put a 1 in the 8's place, and we are left with 3. We now ask, how many 4's are in 3? Well, 0. So we leave it as is and put a 0 in the 4's place. We ask, how many 2's are in 3? And we get 1. So again, we take 2 out and are left with 1, and put a 1 in the 2's place. Last, we ask, how many 1's are in 1? And we get 1. So we put a 1 in the 1's place. That's a lot of 1's. We are now left with binary 1011, which is equivalent to 11 in decimal. Once more, with a slightly harder number. Bring back 234. This time, we will use 8 bits. So, we start out with asking, how many 128's are in 234? As a side note, you should always end up with less than your base in the place value. If you don't, you aren't using enough digits to hold it. So back to the question. The answer is we have 128. So again, we take 128 out and we are left with 106 and put a 1 in the 128's place. Next, we ask, how many 64's are in 106? Well, there's 1 again. So we take out 64 and are left with 42. And we put a 1 in the 64's place. We ask, how many 32's are in 42? Well, there's 1. So we take 32 out and are left with 10. And put a 1 in the 32's place. We ask, how many 16's are in 10? Well, 0. So we leave it as is and put a 0 in the 16's place. We ask, how many 8's are in 10? Well, 1. So we take out an 8 and we are left with 2, and put a 1 in the 8th place. We ask, how many 4s are in 2? Answer, none, so put a 0 in the 4's place. We ask, how many 2s are in 2? Well, 1, so we take a 2 and are left with 0, and put a 1 in the 2's place. And just for completeness, we ask, how many 1s are in 0? Of course there are 0, so we put a 0 in the 1's place. This leaves us with 111011010 in binary, which is equivalent to 234 in decimal. Now, that was a lot of work, but you should find a way for you to convert quickly with time. But now, we have a real monster, hexadecimal. If I say hex, that's just a short version for hexadecimal. Hexadecimal will be similar, but we will be working with larger multiples as it is a base 16 system. This means that a single digit can denote numbers all the way up to 15. For 10, 11, 12, 13, 14, and 15, the symbols used are A, B, C, D, E, and F, respectively. So when we count in hexadecimal, with one digit, we can count all the way to F, which is 15. This is still the ones place, counting how many ones we have. Like with the other systems, if we add one more to this digit, it will roll over back to 0, the first symbol. So we add another digit and carry over the 1. This is the 16s place and counts how many 16s we have. So hex 10 is 16 in decimal. The next digit, if we had one, would be 16 to the power of 2, or 16 times 16, which is the 256's place. So let's go ahead and convert 234 decimal to hex. Now, this is a little different and more difficult because we are taking our standard decimal system and converting to a higher one. The following math does the same thing that we did in binary, just dealing with the complexities of a higher order system. However, it is still asking how many 16s are in 234, and then asking how many 1s are in 10, which is what's left over. So, we look at 234 and say, okay, let's divide 234 by 16 to find how many 16s we have. Well, we get 14, so we have 14 16s, and we get a remainder of 10, so that's what's left over. This will become hex EA, where E is the 14 and A is 10. Let's do one more complex example, just so mathematically you can see how this works. One that needs 3 hex digits. We will choose 3,965. First, we divide by 256 to find out how many 256's are in this number, and we get 15, remainder 125. So we put F, which is 15, in our 256's place. We now take what we had left over, which is 125, and divide by 16 to find out how many 16s we had. And we get 7 with 13 left over. This means we have 7 16s, so we put 7 in the 16s place. Last, divide our remainder 13 by 1, and we get 13, which is symbol D for the ones place. So in total, that's F7D. Again, this is just the same as asking how many 256's there are, and then asking how many 16s there are, and then how many 1s, just like we did in binary to decimal. I'm going to be honest though, I had to use a calculator on this, which breaks the rules of my challenge of using another computer. So why would we use hexadecimal? Well, let me cover hexadecimal to decimal, and then I will show you the magic of why we use hexadecimal in programming and computers. So let's take a number like 3a in hexadecimal. We can convert this essentially the same way we did in binary. We look at it and we say, oh, we have 3/16, which is 48, and then we have a1s, which a equals 10, so we have 10 ones. If we add them together, we get 58. I'm not going to go too in depth on how to do hexadecimal to decimal because it's essentially the same as what we did before. But again, I used a calculator to make it easier. So why would we use hexadecimal? Well, the magic comes from converting binary to hexadecimal and back again. Because this is so easy, you will rarely convert from decimal to hexadecimal or from hexadecimal to decimal directly, but rather go through binary first. The reason for this is each 4 bits, also known as a nibble, map directly to a digit in hexadecimal. This means we can take a binary number and split it into groups of 4 bits and work with these groups separately. You may have noticed that in hexadecimal, the second digit is the 16s place. This is the same as the 5th digit in binary. This means the first 4 bits in binary must be able to have the same values as the first digit in hexadecimal. Likewise, the next digit in hex is the 256's place, which is the same as binary's 9th digit. So bits 5 through 8 must hold the same information as hexadecimal's second digit. That's why this splitting and one-to-one mapping works. So let's make a table of the binary to hexadecimal mappings. Now, let's take 234 as an example. Earlier we found that this equals binary 11101010. Let's split this number into parts. Taking the top part, we get 1110. And we see this maps to hex E. So we put E in the most significant digit. Taking the bottom part, we get 1010. And we see it maps to A. So we put A in the least significant digit. We end up with EA, which is exactly what we ended up with using the calculator method. And to go back, let's take hex F7D, which from earlier we know is 3,965 in decimal. Let's split it up into 3 parts and take it digit by digit mapping to binary. We see F maps to 1111, so we put that down as the upper 4 bits. We see 7 maps to 0111, so we put that down for the next 4 bits. Lastly, we see D maps to 1101, so we put that for the last 4 bits. This gives 111101111101 when put all together. If we do the conversion to decimal, which I have quickly done here, we get 3,965, which is exactly what we expected. You may have noticed that the reason we use hexadecimal is that what used to take 4 digits in binary now only takes 1, or what took 8 now takes 2. When using characters in programming, this uses significantly less space and is faster to read. As we have seen, the conversion to binary is pretty quick. So, saving on code space and data space is a really good reason to use hexadecimal. So, now that I have fried your brain with all this new knowledge, allow me to confuse you with just one last thing. The number you are looking at right now is 234. Before you think I've gone crazy, the most significant digit of this number is on the right, and the least significant digit is on the left. You will rarely see this, but in binary and sometimes hexadecimal, it can happen. The switches I use to program my board have the most significant digit on the right for binary, so I thought I should mention it. After all this, you should understand how to get from one common number system to another. There are some other number systems used in programming, such as octal, a base 8 number system, and a base 4 called quaternary. Though they are quick to figure out if you need them, as they are just simpler versions of hexadecimal. You should also have enough knowledge to work in any base number system if you really wanted to, such as base 5. Though why you would, I'm not really sure, unless you're in a knowledge bowl. Anyway, that will be it for this video. Leave a like, a comment, and subscribe for more. Until next time.